Okay, got people joining us. Give it a couple more seconds. Welcome, everyone. Housekeeping note, if you haven't heard this from me a few times already today, please make sure that your first and last name is listed in the participants section. You can find it by hitting participants, finding your name, and you can click on it to rename yourself. This helps with reporting continuing education credits so that I know who receives it, especially if you're using like just a first name. Sometimes there might be multiple people in the meeting with the same first name. So if you have not had a chance to update that, look at your chat. I will be sending messages to anyone who I'm not sure who you are, asking you to change your name. And with that, I would like to introduce Tyler Swore with Performance Roofing Associates. They are the sponsor of today's session, How to Make the Most of Energy Modeling from SD through Post-Occupancy. So with that, Tyler, I will hand it over to you.
Thank you so much. And thanks for having us. Performance is always very excited to sponsor part of this event. I know we'd all rather be in person, but we'll get there soon enough. So I'm just going to steal a few minutes of your time here before we talk about energy modeling.
Uh-oh, it looks like Tyler might have some connection issues.
Yeah, he's frozen for us too.
Yes, and not in a great facial position either. You know, poor Tyler. All right, maybe give him another second or two and see if he comes back. Does not look good. Okay, well, we might have to just shift gears. Looks like he's been bounced completely. So I don't know if Maddie, if you're ready, we'll maybe switch gears. And if Tyler comes back, we'll put him on the back end.
Oh, looks like Tyler's back. Tyler, can you hear us?
Yeah. Can you hear me?
Yes.
Yes.
Looks like I'm in an
Okay, I have muted Tyler. I know he's kind of breaking up. So maybe we'll get started with the presentation and we'll touch base with Tyler on the back end.
All right.
Okay.
Yep, we just got a confirmation note from him. That works.
All right. Sorry about all the technical glitches, everyone.
Okay, so well, again, just like Kira mentioned, this is how to make the most out of energy modeling from SD through post-occupancy. Go ahead, Maddie, and we can jump into this. So my name is Joe Hofstetter. I'm a principal at Karpinski Engineering. We are headquartered in Cleveland, but have offices in Akron, Columbus, Western New York, and here in Pittsburgh. I'm the director of our building performance and sustainability department. So not only do we focus on design along with the rest of the firm, but we take a very specific focus on energy, building overall performance, whether that's indoor air quality, energy efficiency, commissioning, et cetera. And then we also have a very large focus on our sustainability projects where we provide green building certification, and other specific work around sustainability. With me is Maddie Didos. Maddie is a engineer with an energy specific focus for Karpinski and does a lot of our energy modeling and has a strong background in energy modeling and design. So together we're presenting this as a group today, and I think we're pretty informal and want to try to move back and forth between the two of us. But please feel free to reach out if you have a comment, and then we'll of course have questions at the end as well. So for our agenda today, we're going to hit a little bit about what is energy modeling as it pertains to our discussion today. Getting into some of the specifics and details about what it is, what it's not. We want to talk about energy modeling through the life cycle of the project. And we're going to break that down into an early stage, mid stage, and late stage of the design. So this coincides with the ASHRAE 209 guideline, and we'll explain that in a little bit as well. So to start us off, and I think Maddie is going to add a link if he hasn't already, but we wanted to ask, just get a feel for the room, if you will, and ask who on the call or in the meeting here has had some experience with energy modeling on projects, and then what is that experience been like for those projects, and how has it supported and impacted the success of the design and the construction of the project. So Maddie, do we have that link in there?
I posted in the chat.
Yes. So I'll give everybody a chance. If you can click on the link, then when we're going to keep going into our our learning objectives, and we will come back to these questions if you want to multitask and try to answer those while I continue to talk. Let's see here. We send to everybody. So Maddie, it may, yep, okay, sent it again there. I think we posted it early, so before everybody was on, it may not have been available, the history of the chat. So hopefully that works. Please send us a quick message if that's not the case. Okay, so our learning objectives for this, we try to stay consistent with kind of the AIA template of presenting for this. And the major items that we want to hit on is talk about kind of the different motives of energy modeling, and we'll get into what we mean by that. But what's driving that energy modeling is being asked for on a project. We want to explain what the tool is best used for at the different phases of the project, how it can really impact a project in the right way, and what it's not. Talk about kind of some of those early models and what we can expect out of them versus some of the latter models that are going to have a lot more detail to them. We're going to hit on the building components and what really are those key items that impact the overall performance of our building. And then finally, throughout the presentation, we're going to hint at the tools, both the energy modeling software platforms that are available to use, and also the tools within those software packages and what that means. So Maddie's going to jump out of the presentation here, see if we can refresh and see if we had any responses, if that worked at all. Oh, awesome. Thank you for doing that, everyone. So So yeah, this is great to see such a large number of responses about optimizing the building performance. I think that's really the best value that we get out of the tool. We often do see a lot of lead projects, and it might just be to check the box, or it might be a combination of those two items. Life cycle costs, definitely, that's consistent with what we usually see, where that is a little bit larger investment, involves a little bit more involvement from other parties, whether it's the owner, the CM for pricing, things of that nature, to get good information for that. And then what's our experience been? It looks like above average, so that's good. And hopefully, what we can cover today will, help create the right questions and right interaction between an energy modeler and your teams to improve the value of that on a job. So thanks, everybody. So to get into kind of what is energy modeling, I know this is, it's kind of a silly question to ask, because I think we're, especially with the results there shown from the poll, everybody is fairly familiar with what it is, but I wanted to define it in a way that that's going to help explain and create the conversation about the rest of the presentation. So I think what we see a lot of when asked for energy modeling services on a project is it comes down into two categories. And what we've kind of shown here is we have really what is energy modeling being brought to the table because it's being mandated in some way, or do we have an owner, design, and construction team that is really motivated to do something and optimize something? So, a couple key terms that you can pull off of this slide is, when we're talking about a mandate, and I know for our offices in Ohio, we have a lot of our city and state buildings, especially like our K through 12 schools, that are required to get like a LEED silver. And there's a lot of, obviously government buildings require some level of green certification to qualify for their compliance. So in some cases, we are just flat out mandated to do it. And we often kind of get pushed to the position of just evaluate what we've designed, make sure that we're meeting or exceeding our code verification, and provide the information for the verification for LEED or whatever third party is providing that third party review. Where I think it's more of an advanced tool, an advanced process throughout the design and construction phases of the project is when we really, instead of evaluating, we're looking at optimizing. We're trying to really do the best we can with the building, and that energy performance is a very high priority that competes with other priorities for the building. Comparing parametric runs, really using the tool to not just run one comparison to code and it is what it is, but looking at multiple iterations and seeing those results and reacting and making changes to those results. And then, this kind of aligns with that life cycle cost analysis, or, our payback analysis, if you will, but justification versus verification. Justifying why we're doing what we're doing for the building, why we may be spending more money in first costs to benefit the overall operating costs of the facility, things of that nature. So that's where I think we're going to try to talk about how to get more into the motivated and advanced usage of the tools to better the team. So why do we need to kind of move in that direction? This may be familiar to some, but with 90.1 going back to we have 2004 listed here and up through 2016, and there's now 2019 available as well. We're seeing a 33% reduction in EUI of a code compliant building from 2004 to 2016 ASHRAE standards. So when we really started doing a lot of green building certifications, you could rely on the improvement in lighting technology of whether it was low power fluorescence or moving into the LED era, if you will, that there was always a big gap between what code requirement was and what our lighting performance could be, just based on what was good practice. Same thing with equipment efficiency. And there's a lot of things like in the sequence of operation that we could implement in an energy model to just do better than code. And if you will, outsmart the standard. And as the code is improved from 2004 to 7, 10, 13, 16, that margin has reduced significantly, which puts a much heavier burden on that integrated design process of making sure that our building envelope aligns with our lighting and HVAC systems, that we are very conscious about what our plug loads are in the building, and that we can best represent the building and look at it holistically over all of those different energy consuming components.
So we talked a little about what energy modeling is and why we're doing it. Now we're going to get into the how, kind of the nuts and bolts of the process. So really the goal of our energy model is to translate all these inputs that you see on the left side of the screen, whether it's things with our envelopes and things with our occupants, our lights, our HVAC equipment. There's a lot of different values that kind of go in the input side. And we want to translate that into one or two outputs, which we'll call key performance indicators. And that's what you see over on the right. On annual energy consumption, our cost, our peak heating or cooling loads for sizing of our equipment, or maybe how many hours out of the year we don't meet the thermostat set points. A couple things that I want to make note of is when we're building a model, especially early on, a lot of these inputs are going to be assumptions or like a best guess, where we kind of work together as a team, architect, engineer, modeler, owner, and we're doing our best to see, what do we think this wall is going to be? How do we think the building is going to be used when we're early in the process? But the accuracy of those assumptions is going to affect the accuracy of our outputs. So number one, everyone in the team has to put their heads together to make good guesses to get valuable results. And number two, those could change between what we assumed and then how the building is actually used. Another thing that's not shown that I wanted to mention is our weather data. So usually to build an energy model, we'll use kind of an average year of the past 30 years. And it's meant to be a decent general projection, but of course, not really to match the reality of the next year of weather. So the tools. For the longest time, the Department of Energy had DOE 2.2, which was basically all the math and the physics behind an energy model. And eQuest was the free user interface that you could use to build the model and run all these calculations. Carrier, HAP, and Train Trace are both load software programs that had some limited energy modeling capabilities. But really the cream of the crop now is Energy Plus, and that's the Department of Energy's updated version. And it really just offers much greater flexibility in terms of the number of systems you can model and accuracy in the models themselves. And all the products listed under that Energy Plus box are just different front ends that run that kind of the Department of Energy calculation. From an architect's perspective, you really just want to make sure your consultants are using the Energy Plus tool.
There was the DOE really created both the engine and the user interface with eQuest and DOE 2.2. And they really refined that they only had the funds to build the engine and needed to rely on the private sector to create the front end tools. But they all have a very similar embedded engine that are running the results out of them if they're the Energy Plus platform.
So now we're kind of going to take a quick look at where's our energy going and what can we really do about it. And the piece we're going to focus on most in this pie chart is the light blue section over on the left. And that's all occupant related equipment, whether it's office, refrigeration, miscellaneous air compressors for a lab, anything. And this accounts for over a third of the building's energy use. Now, as architects and engineers, that's kind of outside of the scope that we really have control over. We can make recommendations to the owner to buy more efficient equipment, but really we're only working with 2/3 of the pie. This just shows a similar graphic, except showing carbon dioxide equivalent. And since a lot of that equipment is electric, then it goes up to about half of our annual CO2 emissions are from that occupant related equipment.
I think, what some real world feedback of the value of this information and explanation of this information is we often hear the comment of, for example, like a healthcare organization where they have a large building stock. They have a lot of existing buildings already. And I've seen projects, both that we've been involved in and ones that we've been completely uninvolved in, where there's complaints that a new design building's energy usage can actually be higher than maybe their old original building. And some of that could be because the old building wasn't meeting the same code or comfort requirements that the new building is meeting. It's a different, apples and oranges comparison from that regard. But it also has a lot to do with, take an OR where a state-of-the-art OR today may have 5+ flat screen TVs in it. Might have a lot more electronics operating in that OR and maybe twice the size. So I even heard the comment from one facilities managing a group with a healthcare group that instead of looking at energy use per square foot, they were actually looking at it per cubic foot, because that was another impact that they were seeing where the ceiling heights, the amount of two-story space in a lot of their newer designed buildings is significantly higher than what was in their 1960 or 1970 building that their new construction is replacing. So that's one example. Another example is we're getting pushed a lot on EUI of what a target EUI is going to be and how that ties into Energy Star comparison, which is really a facilities-based metric versus a design-based metric, if you will, because it really is about how you're operating the building. And back to this is pie is what kind of explains that is there's a significant amount of it that's out of our control. So when we're having conversations with owners, it's important to differentiate what a building is going to consume based off of the operating characteristics and the design characteristics. And explaining that early and getting to a consensus of what our target is going to be. Go ahead, May. Sorry to interrupt there.
Oh, no, great insight. So this is just one example of kind of the amount of impact that occupant equipment can have. This was for a large hotel, and the table you see shows the difference in EUI and lead cost savings between an energy model result with kind of standard elevator and escalator watts per square foot assumptions versus what actually went in the project, which was like state-of-the-art energy regenerative drive elevators and escalators. Kind of want to get across two things in this slide. Number one, you can see in that EUI that just from that one change, that's a very big impact in terms of the amount of utility cost savings that the owner is going to see. And number two, if we make a recommendation that the owner takes us up on and purchases some of this more expensive state-of-the-art equipment, we want to be sure to account for it in our energy model and take that credit when it comes to a lead submission or a rebate or something like that.
So getting into some of the details about how this works through the process, and we're going to hint at like ASH rate 209 is we're going to get into a little bit of the weeds here. And if I can say one thing, at the end of this, and I'll reiterate it at the end, I think we're going to talk about three major points of all these different components of the modeling cycle. And those are sensitivity analysis, optimization, and then finally system refinement. So those are kind of what we want to hit on. And what this slide here is showing is that this isn't just Joe and Maddie coming up with stuff, like that there is a consensus in the industry around what components do make up energy modeling cycle throughout the life cycle of a project. And it really does start like that early stage of SD and DD and can go all the way through late stage construction and post occupancy of the different usage of it. So you'll notice, and I guess we can go on to the next slide here, Maddie, with those different stages, you're going to visually see those impacts as well. So, I mean, we may start off with just a box model. You've probably heard that term before. That's going to get refined into more of the actual shape of the building with some very basic window layouts that are getting us close. And then when we do start to get into the late DD or CD level drawings, we are going to be rendering essentially the exact same building as our Revit model or our 2-spec building design.
So as Joe mentioned, we kind of broke this into our 3 sort of early stage, mid stage, late stage, and assigned different modeling cycles to that. So the early stage is going to happen during pre-design or SD. And really at this point, we're asking and answering some very broad questions, not necessarily testing specific options. So we grouped the first 3 cycles from 209 under this early stage. And the one I've highlighted is load reduction, that third one. And it's in bold because technically to comply with the standard, it's the only one that's actually required. The other ones you can kind of pick and choose to whatever suits your project. But the reason load reduction is required is because it's one of the more powerful modeling cycles. And it's trying to answer this question of what building systems are going to give us the most bang for our buck in terms of energy performance. And how can we answer that early on in the design process? So during this early stage, we're going to try and answer that question. And then along with that, sort of see where should the design team focus their effort and where should the owner spend their money? Because we don't want to spend a lot of time or budget researching or buying a product that's not really going to provide us a lot of energy savings. Now, the answers to some of these questions are probably somewhat intuitive, like, improving our wall is probably going to have a larger effect than improving our roof for a tall building. But what our energy model helps us do is quantify, well, how much more does it matter? Is it twice as effective or 10 times as effective? So going back to that input tool KPI setup, our KPIs, or key performance indicators, are shown over here on the right. And I've listed a number of them: energy consumption, CO2 emissions, utility costs. We don't want to pick too many key performance indicators. We want to pick one or maybe two and then stay consistent with that throughout our project so that we can kind of have a consistent standard to judge our building models by. And in the choice of these KPI, we want to make sure that everyone involved with the project gets some input. And what's more important to the owner? Is it CO2 emissions or is it our utility bills? So we all want to work together to kind of decide this early on. In terms of the inputs, these are kind of all the different levers we can pull. We could improve our wall, we can improve our roof, we could put shading on, window to wall percentage, we could, improve kind of our COP of our efficiency of our heating and cooling system. But really at this stage, we're not looking at specific options. We're more looking at model parameters that we know we could achieve. Like, we think we can get a wall between R15 and R25. We think our heating system can be between 85 and 95% efficient. We don't really care to get into the details early on of how we're going to do it. The tools we'll look at are mainly this sensitivity analysis that Joe mentioned. And what we're trying to do here is take the variables we chose in the previous slide and then answer that question: which one matters the most to our KPI of interest? And how sensitivity analysis does that is we define a range over which all of our inputs can vary. We run the energy model of our building hundreds of times, letting all those inputs vary across their ranges. And then we analyze all those runs together to see which of those variables had the largest effect. And parametric analysis is really just a simplified version of this, where we kind of hone in on one variable at a time.
So a little bit of an example of this, and the thought process that goes behind it is here we had a college resident hall, 600 residents, 170,000 square foot building. The project goals were to be LEED Silver, and as part of that LEED Silver agenda, they wanted to have approximately 30% energy cost savings on the energy performance values. And what really kind of drives some of the decision making is being that this was a campus and that they had the investment in their central utility and plant. They upfront basically flat out said, we are tying this into the district heating system, and we are tying this into the chilled water system. So right then and there, that answers some of our variable questions. It takes off some of that equipment out of the discussion about what are we really looking at, because we knew those were going to be fixed variables and there wasn't a lot to change there. So going back to this familiar image, what we did pull out was, our window performance, whether shading would have what shading would have an impact on for exterior shading and cantilevers, if you will. What our wall performance, roof performance, and then we also put in our light power density for our lighting level or lighting power requirements for the project. So applying the sensitivity analysis, what this essentially produces for our KPI is a result like this. So the standardization coefficient essentially is looking at what Maddie was talking about earlier. How much better does one of these items have over the other? So at this early stage of the project, I think we're used to seeing a CM look at pricing as, okay, what kind of a bucket of money do I have for all of these different components of the building? I've got so much in for the skin of the building. I have so much in for the interiors of the building and the quality that goes along with that. Our mechanical, electrical, plumbing systems and how much cost per square foot I'm going to include on that. And I think what this tool really allows you to look at is, okay, if I'm looking at a cost per square foot or a bucket of money that I need to identify for a specific system within the building, I can use this information to say, we should be investing more in our window U-value performance and our overall window performance. So if that's X amount of dollars per square foot that my CM puts out there as your average system, and I have specific energy targets that I'm trying to achieve with these levers, I want to make sure that that's X plus a certain percentage, 20% better, 30% better than maybe what my original budget was. And things like light power density, roof R value or wall R value, maybe we reduce some value there to try to make up for that. If energy performance is our key item that we're trying to achieve here. So when we do apply cost to some of these items, I think this is some of the other results that we'll see is we can compare kind of our first cost to our energy savings of those incremental or parametric runs, if you will. And this is pretty similar to what we see often where, for example, in the graph A here, we've got very much of an exponential curve where we're going to get a lot of bang for our buck, if you will, at the lower end of this curve. And as that curve starts to steepen, it's going to be a diminishing rate of return. So finding that sweet spot, that apex of the curve, I think is important to say, all right, this is as far as we should take it, and we need to cut our losses. Look for energy savings in other categories. In example B, what that's really kind of showing is, for example, a wall system, where as you increase your insulation through a certain wall construction, you're going to continue to improve on a linear rate until you get to a point where, all right, now we have to start thinking about a new way of constructing this wall to be able to include more insulation, or more layers to that wall system. So you're going to have those points where we're going to break through thresholds. And if you do break through that threshold, you should kind of take it up to the limit and then try to stay, within that range, so that you don't find yourself at a point in the curve where you're not getting the best return on your investment.
So moving to the mid stage, this happens more in DD and CD phases of our project. And we're trying to take what we learned from the early stage modeling and now test more specific options. So we've grouped these 4 modeling cycles into the mid stage. We can look at our HVAC selection, where we compare, different types of HVAC systems. Design refinement is where we kind of hone in on the control sequences. Number 6 is one we're going to talk about the most today, and that's integration and optimization. And that's really how to balance multiple things that we care about. How do we weigh our first cost against our energy consumption? And we could also use our energy model in number 7 to evaluate VE items. So kind of looking at that optimization, we're trying to answer 2 questions. And instead of asking what matters most, like we did early on, in the mid stage, we've kind of transitioned to asking what's the best set of options, or what's our best building design. And then using that optimization tool, how can we balance multiple key performance indicators? Our KPI are pretty similar. As I mentioned before, we want to be consistent with our choice of KPI throughout the project. The one that got added at the bottom was life cycle cost. And that's just because at this point, we now know enough about our system alternatives to do a life cycle cost analysis. Before, there were too many just theoretical parameters to test option A versus option B. Our inputs have also stayed fairly similar since the early stage. Just instead of using model parameters like a wall R value or a heating system efficiency, we've transitioned to here's 3 walls that we could actually build. Here's 3 HVAC systems that we're going to design, and we'll test those specific options. So as I mentioned, the optimization tool is really what we're going to dive into. And the process of that is similar to what we discussed with sensitivity analysis. Instead of defining a range, we're going to define a set of design options for each one of our inputs. We're going to choose 2 KPI instead of 1 that we want to optimize. We're going to run hundreds of energy models, letting all our inputs vary once again. And then we're going to look at that subset of runs that performs the best at both KPI simultaneously. If we're really good in one but really bad in another, then that's not going to be an optimal run for us. We're going to look at where we do the best at both.
So trying to understand optimization and the value that the tool can bring is, we're looking at a very simple example here, where if we just ask the question of the design, base design, alternate 1 and alternate 2, which of these systems is going to be the best energy operating system, it's pretty straightforward in your answer. That alternate 2, with your best wall, your best window, your best lights, and your best HVAC system, you're going to get the best energy performance out of the building. So we know that's not a hard question to ask. But when we look at that same question and we put in multiple variables about what is the best option to go with that has a first cost impact of less than X amount of dollars, or percentage of design cost, then the question gets really hard to answer. So that's where the optimization comes into play, where we can start using the tool to run all these different what if examples to help us find that solution. And sometimes that solution is not intuitive, and that there's multiple answers to it. So if we take all those inputs that we are kind of talking about, we run the optimization and we focus in on 2 KPI, then we're going to be able to graph our results of all the different ranges of all those different inputs. So in this case, what we're going to talk about is the total source energy consumption versus the peak cooling load. So you would think that these would go hand in hand, but they actually don't always, it doesn't always work out that way. So, when Maddie talks about running hundreds of models, I hope that doesn't intimidate or turn you off from the idea of, how we can fit into the project. The tool allows us to do that instantaneously. So, we're putting this information in, and that's where the value of the tool really helps support us versus the older versions of eQuest that, 15, 20 years ago just didn't have the power to do that. So if we run this scenario, what we see here is we get basically an ink blot test of all those results. So you can see you've got your cooling load on your y-axis, and then you've got your primary energy consumption on your x-axis. And with that, all of those little dots are those hundreds of runs that we create. So if you didn't do this and you want to try to get the best out of both KPI, you may find yourself short because you can have a very good reduced cooling load in the upper left-hand corner there where the arrow is pointing, but it's not all that great from optimized energy, but it's got a pretty high cooling load. Whereas the arrow on the lower right-hand corner has a great cooling load to it, but doesn't have very good overall energy performance. So real world example of this could be the shading coefficient of your glass or the exterior shades on your building, where they're helping reduce your peak load in the summer. But what you might actually be hurting yourself with is the reheat load that you're dealing with in the winter. So the free solar heat that we gain in the winter for our climates might outweigh the cooling benefit that we get in the summer. So overall energy may be higher, even though to design the best cooling system that we could put in. The reality is the best of both worlds exist in this example, where we're down in those like 3 little red dots you can see at the bottom left-hand corner. We're going to talk a little bit more about those, but those are optimizing both our overall energy consumption and our peak cooling load capacity. The funny thing about those examples is we have 4 of those little dots that were down in the corner of the Pareto curve of our results. And you can see here, they get to those results all fairly close together in the first 2 columns of the chart here, where we're right around 6 million kBTU annual energy use, and similar load characteristics on our cooling load. But our light power density, our orientation, our window to wall ratios all have some differences to them, which shows that you can have different ways to achieve the same building performance with very different designed buildings. I think the one that jumps out the most to me is like the lighting power density, where in some cases we could have twice the amount of light power density in a building and still get to the same results if some of those other parameters are adjusted, as you can see here in the chart. So how does this apply with life cycle cost analysis? I think what's important to know is oftentimes we're extracting the information out of the energy model and applying it in some other tool, whether that's some commercially available tool or private tool that the energy engineer may use on the side. But that's where we're trying to bring first cost and annual energy cost, which makes that simple payback analysis, and also take into the financial mechanisms of time value of money, escalation, interest, and then maintenance costs, equipment life expectancy. Those things are very important to communicate and work out as a team, work with the facility side along with the construction side of from an owner's perspective, and get their feedback to get to real world information that can be applied to that part of the tool. This is just an example of what you can see with that, where you see we've got our first costs, we've got our annual utility costs, in this case 2 different utilities of gas and electric. You can apply non-annual maintenance and replacement costs of the project, along with annual maintenance costs that are more reoccurring costs to those components of the project. And all of that information kind of comes together to create the results that can make decisions on. In this example, we had, like if you look at the green and red lines on our chart, we were able to throw out the worst case and best case scenario because they were just really out of our range. And then the decision came down to kind of that green and red line. And the payback on that from a return on investment of an LCCA was about 15 years. So going back to the owner and understanding, is that within the life expectancy of the systems involved? And does that meet the kind of the return on investment that financially the organization would be happy to make? Go ahead, Maddie.
So moving into the late stage, this is in the construction post-occupancy phases of our project. And we're kind of past the point of making any decisions at this point in the project. We're kind of just seeing how well we did. So the modeling cycles that are grouped here is our as designed, which is used for LEED certification and rebates. Similar to how we look at VE items, we can use the energy model to evaluate change orders. We can look at as built. And then the final cycle is post occupancy, where we move out of that theoretical and we start comparing our energy model to how the building is actually functioning, looking at the utility bills. So the few questions we'll try and answer: how do we compare to a code compliant building? How does a single change affect our energy costs? And then, how well did what we projected match what we're actually using? And going back to that pie chart, talking about the as designed energy performance a bit, as Joe mentioned earlier, the difference between ASHRAE 90.1's requirements for comparing baseline and proposed energy models in LEED is different than the Energy Star score. In 90.1 and LEED, you're kind of taking that bright blue piece of the pie out of the equation and keeping that the same between your baseline and proposed models. And you're only looking at the other 2/3 of the pie, so you can really evaluate how well the design team did on their portion. The Energy Star score, of course, takes into account the entire pie. And then the other tool we use in post-occupancy is calibration, where we can sort of fine-tune the occupancy and the weather data of what actually happened to our model.
So I'm going to hit on this rather quickly here, but this is kind of the example results that you would get of comparing from an ASHRAE perspective an Appendix G designed baseline building to a proposed building, and what that looks like is what we're putting into like a LEED tool to identify those savings. But to be mindful of time and kind of wrapping up the last few slides here, I think the two key things I want to hit at for this later stage part of the process is trying to give some more real world examples. And one is I had a project where we had a significant continuous insulation wall system, and by design and by specification, it used more of a plastic or composite clip system that really enhanced the continuousness, if you will, of that insulation. And during construction, it was determined that was a little bit harder to get to. The lead times were longer and costs were a little bit higher. So it was proposed to put in more of a channel system that used like an aluminum channel or some kind of metal channel system to hold the continuous insulation in place. And not thinking much of it, they were going to approve it, and they just happened to ask for our opinion of it, and we ran it in our tool. And because of that bridging in the insulation, it reduced our wall insulation from by about 30 or 35% in its overall performance, and actually had a pretty big impact to the overall energy performance of the building. So that's a perfect example. When there's RFIs coming in, if there's change orders in, don't forget about the value that this tool can bring in helping analyze that and do a change like that. That's really pretty quick to make, run the results and provide that objective feedback to the team of why we can or cannot move forward with a change. Finally here, calibrating, Maddie made a mention earlier about weather data and how we kind of go off of an average. And in the later parts of this tool and how we can extend the usefulness of this tool into occupancy is calibrating it to actual real weather data, real world situations. So after that first year of occupancy, we now have that historical information that's available internationally of being able to pull that weather data of the last historical year. And we can actually create the hour by hour analysis and compare it to real world, real time situation and see how we perform that way. It's a great way to tweak the building through the commissioning process and continuous commissioning process to make sure that it's performing the way that we intended and designed it to. So I guess to wrap up, what I just wanted to hit on and just reiterate, like I kind of mentioned I would, is, really our goal today was to talk about the value that integrated design and integrated energy modeling and services can apply to the team. And if there's anything you pull away from key things that are modeling person on the team is how are we looking at our early stage, mid stage, and late stage energy model inputs and outputs in regard to our sensitivity analysis to help make those early decisions, optimize our overall performance of the building through that mid stage, and then finally troubleshooting, getting close to our real world results as we can. And then, so with that, we probably ran a little over and didn't leave too much time for questions. And I know we definitely want to give Tyler a chance to jump back in if he's still on the call. But thank you for everybody for attending and giving us an hour of your time today. Maddie and I both really appreciate that.
I do think we have a few minutes. If anyone has any questions, feel free to unmute yourself and ask.
I'm still absorbing everything.
Okay, I guess that means no questions. I would also like to thank Performance Roofing Associates for sponsoring the session. Tyler messaged me and said his internet is completely out now in his entire house, so he will not be back. But we want to thank them and acknowledge them for being a sponsor. And if there are no other questions, then I think we will wrap this session up. Thank you, Joe and Maddie, for joining us.
Thank you, Kira, and I appreciate some of the comments coming in. And please reach out to us if you have any more details you'd like to talk about. Love to help you.
Thank you.
All right. Thank you. Take care, everyone.
Thanks, everyone.